All right, so the last item of discussion was again in doing this series summation. We looked at several transformations for the same program that involved introducing padding was one step to avoid the fault sharing. Then we looked at various ways to implement the final summation by doing atomic or critical. And the last thing we discussed before we broke for the break was to make the final summation also go in parallel. So remember that we started with parallelization, where multiple threads were running this block of code, and different threads were engaged in different iterations of the for loop also. So there was parallelism even in this for loop. Different codes were running, different threads were running this for loop in parallel also. But finally we were bottlenecked when it came to the final addition. But there we still don't have parallelism in this version, but at least the critical or atomic variables are preventing the threads from stepping on each other's work. Anywhere where multiple threads are writing into one variable, in this case pi, if thread 1 does a write, thread 2 does a write, all this, it's not a write, it's not doing a write, it's doing a plus equal to. So if I have, let me open a new page. So if I have pi plus equal to sum produced by thread 1, pi plus equal to sum produced by thread 2, all these running in parallel, it's not very clear what to expect. What is involved is a read of pi, a read of S1, addition, write back into pi. That's all going in parallel with read of pi, read of S2, addition, write back into pi. This is again saying the obvious. In concurrency, with concurrency, these are the minute steps. So you can now think of all these steps interleaving, much like the deck of cards we mentioned. So maybe we have read pi and S1, done the addition but not finally done the write back. Meanwhile this has been read, this has been read, this addition is done, this write back has not been done. Or then both threads are seeing the old value of pi. But in another situation, maybe this read has happened, this read has happened, addition has happened, write has happened, and then this read happens, then this write happens. You see, so there's a difference there. The correct answer would be obtained in this case when you read fully, add and write back. Then if you pick up that value and add and write back, you are getting cascaded additions benefit. But if you did the other way, where all partial answers were read, the old values were read without any updates, then only one update will be seen. So you will miss many updates. Is that clear? Yeah. You can miss several updates if you all read the old value, add, and then write back. Then the last writer survives. That's not what we want. We want the combined effect. So all those problems are eliminated by putting atomic or critical, because in an atomic or critical, it is as if you did not interleave. That's the effect atomic or critical gives you. So the entire activity completes, read, update, and then another read and update. So the entire serial addition benefit is obtained. But there is a cost to that. It serializes the execution at that point. But also remember the pink elephants from yesterday. You may not even get the effect of one of the partial updates. You may get a funny value. You never ever would get it under any interleaving. So the pink elephant values or funny values, like I mentioned yesterday, are values that are a result of compilers optimizing the code in various ways. Compilers hold values in registers and Sometimes they tear a word into 2 half words and then put 1 half word in a certain variable location. Finally, they'll clean everything up. But compilers have no idea that you intended to run this code in parallel, so you may start seeing these torn variables. So you really see bizarre values. Herb Sutter, you should really, I don't have time to show you the details, but look at the talk called Atomic Weapons. By Herb Sutter. From Microsoft. That's an excellent talk of an hour in length, and he makes it extremely clear to today's programmers, saying, look, languages like C and C++ are not today the languages you knew before 2000 or even before 2005. Those languages have changed significantly, and the main additions are compilers have a contract not to play with atomic variables if you have properly annotate them. And this message is difficult to get across suddenly, right? Because if misinformation is there in old books, it takes at least 15-20 years to purge it. So the more you listen to these talks and get caught up, you will be more equipped with better programming skills and the use of modern languages like C++ 11, C++ 14, C++ 17. These are extremely good standardization efforts by the brightest minds out there. And C also has C11, they call it. It depends on the compilers. Many compilers did not support C++ 11, C++ 14, but now GCC supports C++ 7, C++ 14. Intel compiler also supports these standards. So anyway, so that's the detail about atomic. Okay, so reduction is what we discussed the most recently. Reduction gives you the best of both worlds. Not only is this partial summation getting done by the threads, but the reduction tree also is getting evaluated. So in a sense, there is parallel activity that is producing these input values to the reduction process, and the reduction execution is also done by the OpenMP environment in a concurrent way, meaning these 3 additions are all being internally scheduled. So you get the best of both worlds, and you didn't have to declare the sum to be a critical variable or atomic and put it under atomic. The sum is automatically treated as being safe as the effect of the tree addition. How this reduction gets carried out, of course, gives you the floating point surprise. Again, remember the lecture from yesterday. Depending on how you ran a certain OpenMP program, 100 different executions, you saw different values. That can happen because the reduction tree's shape is not fixed. It may, if the scheduler is busy with some activity and gets interrupted, maybe the reduction tree will be a left-leaning tree like that, and another schedule might produce a more balanced reduction tree. And I also mentioned the point that floating points are an approximation to real numbers, but floating points are more true to the real number semantics if floating point addition or operations are done more balanced. Any skewed addition or balancing or addition or other operation has the problem that floating point addition or multiplication are not associative at all, and even some small values may dominate. So I said there is a big value and a small value, the big value and a small value. At some point the big value becomes so big that it starts ignoring the small values, so then the big value saturates. Whereas if you have small values, they can really grow to the true sum or close to the true sum with balanced addition. These are all points that, again, you don't need to worry about on a day-to-day basis, but I can pretty much tell you that it's only people like me who worry about it a bit more. Many other courses over there give importance to performance tuning because they are performance tuning experts. I'm a correctness expert, so I look at correctness problems. So you cannot get everything from this course. You have to get what I can offer better. You take that, take another course, go to a performance guys course. So get the best of all ideas from every course. That's usually how parallel programming is learned. You have to read a lot of code out there, look at a lot of clean code from experts. That's how you learn programming, right? I mean, we all learn programming by seeing who writes the best program in a certain style. Get their codes, read it for a week, get enough ideas. Then you start imitating. It's like karaoke, right? You start singing and you have to imitate others. All right, so back to single. This is another construct where you can start with, that example is over. We are now looking at Pragma OMP parallel number threads 2, Pragma OMP single. That is like a master, except it's any thread, and there is no barrier here. So that then compute results is done, and the write output. So now you can look at the printout. Read input, it's done by one thread. Compute results, both threads are printing that. The write output, again, single thread is doing it. So you can see from the printout that the single is doing what it is supposed to do. So again, these are all used whenever you want only one thread to be doing something. Yeah. This is a simple illustrative example, okay. Okay, noteworthy points in the next slide. Use of dynamic schedule, chunk size control, reduction variables must be initialized. Otherwise, your answers will be silently garbage. It's a complex standard, so the standard only gives you certain automatic support. You're supposed to know how to use the standard carefully. These are easily committed mistakes. You can always write a checker tool that checks for these. Do you know of a tool called CLint? C had a long time ago a tool called lint. It just checks for the code quality and picks up obvious mistakes. So maybe there's a lint tool needed to pick up all these uninitialized variables and all that. So let us look at how these are illustrated. So now we are going to change the example slightly. This is a calculation of primes, prime numbers. The algorithm is kind of hidden here. It's not a very detailed algorithm, so let us look at it. So prime numbers are those that are divisible by itself or 1. So any number that has a factor other than itself or 1 is not prime. We have to eliminate that. So if a number has a factor, it has to be one of the factors has its square root or lower. Yeah. So if 50, any number who has a factor has to have one factor that is square root of itself or lower. So you don't need to look for factors beyond the square root. So there is a limit established saying I am going to search only up to the square root of that number. So this is a routine is generating all the primes in a certain range. That's the purpose of the code. It is C++. So it has pound include IOStream, pound include CMath, using namespace std instead of stdio.h. Then it has all these printouts or cout, all that. Here's the bug that I mentioned. Don't forget to initialize reduction variables. We are going to use those variables in a reduction clause later. Make sure they are initialized, otherwise you really get the garbage values. There is no support automatically at this point. Those variables are reduced with respect to whatever values they initially contained. If they are not initialized, they can contain any value. So OMP set number of threads, thread count. Pragma OMP parallel. Okay, Pragma OMP parallel. There is no parallel for, so it's parallel. You can add other things around it. You can make the parallel more elaborate by hooking on various things to it. A lot of things you can augment. One of this is num threads thread count. So you can say run this parallel code only with this much many threads. You can say that at that point. Then you can say pragma OMP master threads granted equal to OMP get num threads. Num threads granted is, and then you print out. So that's all. Master. Then you are declaring local variables int j limit prime. Then you are hanging a pragma OMP for. So now what happens is all the threads that are born here are going to hit the OMP4, pragma OMP4. So they will share the iterations of the for. Some will say I'll take this many iterations, some will say I'll take this many iterations, some will say. Default is they all take one iteration. But now you can say how many iterations to take, that's the chunk. I happen to give it one, it could be 4 for instance, in which case each thread will take 4 iterations of that for loop. So that's how you get which allocation, cyclic or block? Huh? Block allocation. Cyclic was what we looked at. Yeah, good. So we can get block allocation that way. Good. So we could have used block allocation in the earlier example. I didn't show that, or maybe it's coming. Good. The primes example instead of padding. Okay, but that's good. So block allocation can be done. Then we have dynamic. That's the new word. Dynamic means use a dynamic scheduling method. I don't care how many threads are allocated for how many iterations. That's somewhat advantageous because if one thread becomes idle, that thread can pick up other iterations. Static schedule means you are statically allocating this many iterations to this many threads. Schedule means these. Okay, so good question. Thank you. So the idea is that this has the potential for work. In parallel programming these days, they say work is available. Who shall do it? Okay. So the for loop has let us say 8 iterations. There are 8 iterations worth of work. Each is an iteration. Schedule means who is going to do these work items. So static schedule means thread 0 is going to statically assigned to do these work items. That's the schedule here. Schedule for work assignment. Dynamic schedule. Dynamic schedule means as soon as one thread becomes free, it can claim another work item. So yeah. Okay. Thank you. Thank you. I should off the wireless. I'll try it once more. Thank you. Thank you. Okay. Yeah. So schedule means in dynamic schedule, it means that thread 0 may do that, and as soon that item, and then as soon as it becomes free, T0 may do that, and then T1 may be working on it, T2 may be working on it, and as soon as T2 is done, T2 may be assigned to do that work item. So it just depends. So the work items are available. The for loop iterations are essentially activities to be carried out, one for each iteration 1, iteration 2, iteration 3, and you run around and pick up work. Okay. So the for loop iteration 25 might be available for execution, and if thread 33 is free, thread 33 may be assigned, please go and do iteration 25 by the OpenMP runtime. Static schedule is going to be a policy by which the OpenMP runtime a priori decides, okay, thread 0 is the one going to do all this, thread 1 is going to be the one doing all this. So it may be that thread 1 has finished all these work items and sitting idle. but thread 1 is not going to be handed this work item because it's already fixed that thread 0's job is to do that. Yeah. So the OpenMP runtime commits to saying you shall do this piece of work, you shall do this piece of work, you shall do that piece of work, and you only can do it even if this group is free. That has a pros and cons. It makes the scheduling overhead lower, and in a sense it's not so bad. Dynamic schedule means you have to have the flexibility of suddenly giving, oh, you do it now because this work is available. Yeah. Dynamic schedule gets used in areas where the variability between the task execution times is very highly variable. Okay. So imagine a for loop where you have iterations where the execution time of all the loop iterations is widely variable. Iteration 5 may have to do some function, mathematical function involving 5, which may happen very quickly. Iteration 8 may involve doing a mathematical function involving 8, which may run for a long time. So if there's high variability, then so another use may be genome matching. I have seen that in MPI. There is a program called MPI BLAST, where MPI BLAST's job is to, I think, do genome matching. BLAST is a genetic algorithm. So maybe there are these genetic work items available as in an array indexed by 0, 1, 2, 3, 4. Maybe when you work on array index 0, that BLAST operation may happen in microseconds or nanoseconds. So that is a process where there is humongous variability in the BLAST process. So in which case you are better off with dynamic schedule. Why tie up threads that are free? They can jump and do the other work. So you have to see whether the loop iterations themselves are all uniformly positioned to carry out the same amount of work, or in this case dynamic doesn't make sense because I cannot think of any case where the square root that doesn't depend on the iteration, okay, like that. So that's the idea. Okay, I think it's clear. Yeah, the high variability of work items created any situation, use dynamic, otherwise static is good. Okay, so now what do we have? So this Pragma OMP parallel says thread team exists. Pragma OMP 4 says all this work is available, but the scheduler can assign it in a static schedule sense. Chunk size control is not exercised here, it's 1, but you can exercise it to be some number like 4. And now this for loop iteration for I equal to 3, I less than equal to primes, I plus plus is carried out. What is it doing? So let's see what the primality is trying to do. It is trying to eliminate any number that is divisible by itself or 1. Happening. I mean, these are all live code readings. I read it a while ago. Let's read it together. All right, primes. Assume the number is prime. That's a Boolean flag. And then we are trying to vote out to see whether that number is prime or not. And if it is voted out and if it is still a prime after this search, then pragma critical, we are adding to the number of primes found. That's the logic of the loop. So which number are we candidate testing to be a prime number? So we are essentially going after all the numbers in the prime range. So any number from 3 up to prime range is candidate to be a prime number. And why I equal to I plus 2? Because even numbers cannot be prime. So it is skipping over even numbers and only thinking of odd numbers being prime candidates. And that for loop is getting parallelized. So you can see that each thread is essentially trying to see whether 3 is a prime, 5 is a prime, 7 is a prime, 9 is a prime, 11 is a prime. That's what the threads are doing here. Each is trying to establish which is a prime number, which is not. So once that number is picked by a thread, it says I'm going to only search up to square root of I. So I'll search up to square root of 3, square root of 5, square root of 7, square root of 11, etc. Then it says, okay, maybe 7 is a prime, then j equal to 3. Then this is trying to see which divisors it has. If it has while prime and j less than limit, if I divide by I mod j equal to 0, prime is 0. So it's evenly divisible. That's when the mod operator becomes 0. Then prime is 0. So then j equal to j plus 2. So it's sort of trying to divide. It's a very naive algorithm. It is simply trying to divide out, let us say 23. It is trying to divide out 23 by all the odd numbers. See what the divisors are. Divisors are j starting at 3 going up to 2. So it is trying to divide out by odd numbers up to the prime. Okay, so once a number has been concluded by a certain thread. So imagine this being done over a very long range, like a billion. The range of a billion is available. Does it make sense to use dynamic schedule here? Let us think. Some numbers is it the case that some numbers are easily established to be primes and some numbers are established to be primes with some more difficulty? In this very simple algorithm, yeah, I can say so, right? If a number is small, it is easily quickly established. If a number is very large, it takes enough time for the divisor process to get there. So there is some variability. It's not a very obvious variability like an MPI blast or anything, but there could be variability of that kind. So maybe it is okay to use dynamic schedule to some extent, but it's not still a very good candidate for dynamic schedule. Okay, but the nice thing is, if it is prime, what are we doing? If it is prime, we are just tabulating two other quantities. This author decided that all primes are of the form 4k plus 1 or 4k minus 1. That is true. Any prime number is expressible as 4k plus 1 or 4k minus 1. I don't know why he's doing that, but he's tallying number of primes of the 4k or 4k plus 1 and 4k plus 3. I think that's some 4k prime minus 1. So that's what variable naming says. So he's tallying that, and finally the tally has to agree. Num p41 and num p43 should add up to the num primes in that range. Something like that is being done in this code. But the higher point is the use of reduction. The use of reduction is being beautifully illustrated here. So how many things are we reducing? That's the interesting aspect of this code. We are carrying out reduction for, let's look at the reduction clause. Where is it? I thought there is a reduction. Where is? No? I thought there is a reduction here. No? Yeah, maybe it's coming later. I will see. So let us look for reduction clauses just by eyeballing. Oh yeah, bug if omitted. So that's why I said there is a reduction variable there. Num primes, num p41, num p43, they are all initialized. Is there a reduction here? No. No, maybe this is, I mean, it's a good remark, but this is where it is. I think this is a cut and paste thing. Okay, I just put it in another piece of code. I didn't illustrate it there. So there is another code that illustrates that idea. Okay, so here, yeah, we are initializing that, but that comment is not very relevant here. So you can, yeah, you can eliminate that comment, but it's still good to initialize it. No, I mean, it's good to initialize any variable. Yeah, it's good to initialize it. Otherwise, we are doing a plus plus operation here. So it's bad even otherwise. You can't leave things uninitialized without a plus plus. Okay, that's good. So here it's just tallying the number of threads. Okay, so now let's use that example in a reduction context. So noteworthy points are: make a chunk size decently large. When you have the ability to parallelize an execution, it's good to create large chunks such that the total number of these chunks just matches the number of threads. So each thread should be working on almost a sequential piece of program. That's the mindset. So if you have a choice of cutting up a item of work into lots of slices, like 1 through 32, but only 16 hardware threads available, that is a poorer organization. You are better off chunking that into 16 such that the chunks are all largely sequential, and that way there is less context to switching overhead. That way there are fewer thread stacks, everything, all the overheads go down, because the degree of parallelism is still that many only. So degree of, yesterday we looked at many concepts. I did not know why I was saying all that, but today it's kind of coming back. We talked about degree of parallelism. Degree of parallelism is a good measure that has to match the amount of hardware threads. We talked about floating point reduction and all the things that is coming today in the reduction of loops. We talked about data races. We looked at atomic and critical to avoid data races. So all those issues are kind of tying up, and I'm sort of happy that there is a connection. Okay, so let's look at this. So now this is the version that uses reduction. So Pragma OMP parallel num threads. Thread stop? No, I can't. It's off and on. Num threads, thread count. OMP schedule dynamic. Look at the chunk size. Pretty chunky instead of 1. So now you can control the chunk size, and the work, the for loops body is split up into iterations, groups of iterations of that size, but the schedule is still dynamic. So once one chunk of work is done, who gets the next chunk of work? Well, whichever thread becomes free gets the next chunk of work. So that scheduling is controlled dynamically, but the chunking can be enforced. But then you put multiple reduction variables. You say reduction, I want to finally do parallel activity but reduce the answers using a plus. And how many reduction processes are going on? Well, there are 3 reduction processes going on. All this is kind of too much syntax, but you can always have a OpenMP reference in front of you, some examples in front of you, then that's how you program anyway. So 3 reduction trees will be concurrently built when you run, and all this will be done by the system. So this search is similar, prime. But now look at this. This is funny. This is fun, not funny. Fun. If prime num primes plus plus, if I percent 4 num p 4 plus 1s, num p 4 3 plus plus. It's almost looking like I'm just doing a plus plus to these variables. But in reality, these variables are being tallied with a reduction. So when you come out, their total accumulation is built for you by the reduction tree. So the threads are all calculating. One thread is contributing to num p41. Another thread may be contributing to num p43. All threads are contributing to num primes. Okay. Whenever a thread finds a prime number, it is contributing 1 unit to here. And furthermore, that thread may contribute to this guy or this guy, because they are mutually exclusive. A prime cannot be both types. So contributions are pouring in from different threads to this and this, or this and this, or this and this. All those contributions are being bound together in a reduction tree. How was it achieved in the previous? Yeah, that was how it was achieved. We just serialized at that point. We said all the threads are contributing, but here this is a single lane bridge. You are walking the single lane bridge, and doing the tallying into numpy and numpy 4.1 and numpy 4.3. Here there is no single lane bridge. It's a multi-lane highway. In the multi-lane highway, multiple threads are computing and tallying through a reduction tree. So 3 reduction trees are being built for you automatically. All that is nice. Yeah. And there is no data race, there is no critical. Okay. Okay, so I ran it for some executions. These are all codes that are worth running. They are short enough to run and study. Points not discussed in this presentation, a lot of points, but we'll look at a few. Private variables, first private, last private. Contrast with TBB will be on Friday. Let's go through OMP syntax chart and see how much has been covered in this series of examples. So now, summary of OpenMP 3.0 C, C++ syntax. So somebody asked about master. Go to this and read or do a PDF search, you'll know. That's what you do. Okay. So download the full OpenMP specification at there. Directives. So let us see. An OpenMP executable directive applies. Let us read it somewhat carefully to see whether we can read a standard now. An OpenMP executable directive applies to the succeeding structured block or an OpenMP construct. Okay, that we looked at. Structured block. It can be a curly brace block or it can be a single statement. Structured blocks are blocks which have a single entry and single exit. Go-tos into the middle of the block and go-tos out of the block are not structured blocks. So those syntactic restrictions are obeyed. Yeah, that's a structured block is a single statement or compound statement with single entry, single exit at the bottom. Okay. Parallel construct forms a team of threads and starts parallel execution. Let us look at a parallel clause. Pragma MP parallel. Clause, 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 and a new line. Then a structured block. Clauses can be if clause, num threads clause, default, private, first private, shared, copy, and reduction. Lot of embellishments and decorations you can put on a first on a thing. So we saw some of it, we didn't see all of it. We saw reduction. Did we see shared? I can check. You can say this variable is shared among the thread team. You can say it is private to each thread team. Yeah. Explicit declaration of shared and private is good. It's good programming practice. It makes the code readable. All that. First private means its initial value is. This is how I remember it. I always check this. I don't use it that often. First private is it snapshots the incoming value, and then it is private. Last private, I think, when that thread dies in the thread team, it imports its private value to the globally shared variable. That's how I remember it, but I am always doubtful when I say this. I had to go and check and look at example. It's not automatic in my mind. It's to quickly initialize the private variable before the thread team starts. Default shared none, you can say default none means I don't assume anything by default. You have to explicitly tell which variable is private, which variable is explicit. That's good programming practice. In some languages like Fortran, there is an implicit none. You don't take anything implicit in. Or default shared. Some people say, oh, there is 25. There are 25 variables, and it's too hard to list it. The code looks ugly, and I know that this is all shared. So default shared, and then they suppress what's not shared. Num threads we saw. Okay, so this means if scalar, so you can apparently give a condition here, and if that condition is true, you go parallel. If that condition is false, you go serial and the master executes it. Well, I don't know. Parallelism for some loops, it can be used. Num threads we saw, default scoping. Yeah, private means private. First private means private plus automatic initialization. Copy in, I think. Copy in list allows a thread to access its master's value. Let's not memorize all this. This is all available. We'll have to see when we can use it. Okay. So if that's at least one read of parallel. That's the most important section. We should use it. I mean, we will use it every time. Okay. Now comes what? My OMP4. So these are all constructs that pick up that offer work items that can be executed by threads. So the loop construct specifies that the iteration of the loops will be distributed among and executed by the encountering team of threads. So whichever team of threads encounters this, it will pick up its iterations and execute. So best is to use parallel for OMP4 inside a OMP parallel, because inside OMP parallel there is a large team of threads that are ready. They will all encounter OMP4 and then they can execute it. If you use this at the top level, there is only one thread, master thread, that encounters it. You don't get any parallelism there. So anyway, so there are these private, first private, last private, reduction, schedule, collapse, order, no wait. Let's read it whenever we need, but that's available. Then comes Pragma OMP section. Section can be offered within a parallel, which means that section can be picked up by section construct contains a set of structured blocks that are to be distributed among and executed by the encountering team of threads. So let us contrast for and sections. For offers, OMP4 does offer sections, correct? Because OMP4 has iterations as the sections. The individual iterations become the sections, because each iteration is like a chunk of work. But instead of for, if you offer this guy under OMP parallel, then what happens is the thread team started by OMP parallel will go and pick up one section, another section, like that. So the work can be heterogeneous in nature. In one section you may launch a missile, the other you may do something. Okay, different activities can be done in different sections. Whereas for means iteration 1, iteration 2, iteration 3, they are all uniform looking. This could be print an output statement, this may be initialize, this may be do a dot product, all these different heterogeneous items can be lined up as sections. Directives, single, task is available. Task is the ability to create work and get threads attached, have threads attached to it. It's a more recent construct. Critical, we saw critical. Barrier, we didn't see barrier. We said there is an implicit barrier at the end of Pragma OMP parallel. But if you want more barriers, just to line up all the threads and do something. Sometimes barriers are inserted by programmers to get a clean starting point where you can clear a timer, do performance counter initialization, do a chunk of work, do a barrier, print the timer, So cease all activities with an explicit barrier. Sometimes those barriers are used. So explicit use of barriers is usually a sign of ignorance in MPI and OpenMP. In an MPI program, there is a paper written where one group argued whether a certain MPI barrier they found in an MPI program was necessary. After a lengthy argument over a week or so, they concluded it was not necessary. They removed it. A year later, the code crashed because the barrier was, after all, necessary. So these stories are there. And ignorance is not bad in parallel programming because it's a hard thing. So confessing ignorance is important. It's very rarely that we all understand a parallel program entirely. Sorry, let us confess. That's the, if I tell that to a civil engineer, they'll be scared. It's very rarely that I understand a building is standing. That's because in civil engineering, there's this thing called safety factor. If your foundation can be proven to work with 1 meter diameter columns, you can always make the columns 5 meter in diameter, and it's always going to improve. In programs, if one assignment is not enough, if you put, or if one skips, there is this, 5 skip statements, that's not improving the program. Yeah? Tasks are construct that I can show the syntax in a separate example, but generally the way in which tasks get used is in a recursive algorithm. So you know the Fibonacci computation, Fibonacci number, that's a classical example. I don't remember the syntax, I can dig up and show you, but in Fibonacci of n is an algorithm where if n equal to 0, then return 1, if n is 1, then return 1, otherwise recursively it is return fib of n minus 1 plus fib of n minus 2. So there are these standard recursion patterns where in a functional programming language, I can type this and show you in a second, where in a Python if I write Fibonacci of n, it'll recurse to do Fibonacci of n minus 1 and Fibonacci of n minus 2. Of course this recursion is exponential, but that's not the point here. But in a tasking situation, you can make these recursive calls become tasks, which are ready work items to execute. But let me dig up some good examples of tasks and show you, okay? I think I don't have it ready, but I don't have internet, but I'll plan it for the lab session today. I will dig up some more examples. But I have seen these common examples where a certain activity can spawn sub-activities in a programmatic sense, and you can allow those to be tasks. Yeah, I haven't used tasks in my class, and it's relatively new. The tasks are not as, it's getting supported in OpenMP, but the reality is that the number of OpenMP codes with the tasks out there is limited still. So when my student developed this data race checking tool called Archer, you will get a chance to use that hopefully. He was looking for examples with tasks, and he found almost none, and he was happy that he didn't spend all his time supporting tasks, etc. Okay. Flush is used. Flush is to post the value held by in the OpenMP's memory space. This is a more detailed discussion. The visibility of threads updates is not immediately available to another thread. Flush is a way to push out the thread's buffered writes into the global space. So if a thread is, how do I introduce the topic? I can tell you certain examples just to give you a suggestion of an example. So if I write a program x equal to, so this is a hypothetical programming language. I can tell you the actual languages where this happens. So this is an example I'm quickly making up to illustrate flush. The idea to keep in mind is there is this notion of a weak consistency, memory consistency. What does that mean? In many languages, these updates, so this is, let us say, being executed by thread T1 and this is being executed by thread T2. If a language or execution system follows the weak consistency principle, then the updates of one thread are not made immediately available to the other thread. It can be delayed. That's the general idea. Even it happens even in the machine instruction level. In x86 assembly code, if two cores are writing to two different variables and then subsequently the cores are reading, that's what is going on here. Okay, so what did I write? I wrote a pattern where I am writing to X, reading X here. I am writing to Y, reading Y here. So when these kinds of cross-coupled write-read situations happen, under weak consistency, it is possible for this read and this read to return the previous value that existed before any write happened. Because these writes are not going to the global memory, they are being parked in a temporary buffer. And that's advantageous because pushing out memory each time is very, very expensive. Cache coherency networks have to wake up and invalidate all the cache lines. Lots of cost. Everything is cost related, energy related. So don't push out unless necessary. OpenMP has also this notion of these hidden buffers. In strong consistency, this never happens. So again, I'm telling you, these are all topics where a lot of old good programming ideas existed. A lot of good computer science thinking has come into the area, and the world now is better for it because these ideas are getting rigorously defined. So that's why these ideas have become established. The reason I told you C and C++ and all these languages have suddenly become better in 2010 on is because they nail down definitions in this area. One of the main contributions is weak consistency is clearly defined, and the holy variables or volatile variables are clearly defined. They were very arbitrary before. So in strong consistency, again, these are ideas you may not play with it right away, but one day you will hear this and maybe suddenly say, aha, it was discussed long ago in this class if you didn't know it already. Okay. So in strong consistency, this example has a certain interesting variation. So let me take that example and execute it under strong consistency. So in strong consistency, all executions look as if they are interleavings, like riffle shuffles, shuffle of decks of cards. So the final appearance of strong consistency should be that, or that, or you see, it should be one of the ways in which you can shuffle the decks of cards. That's the only outcome that is available. So let us follow one of it. In strong consistency, if you follow this zigzag order, did this, did this, did this, did this, then while you are here, or even here, you will see both writes as having happened. Okay, you saw y equal to 2, and you saw x equal to 1, right? Or if you follow another order, Suppose x equal to y equal to 0 here, beginning value. So in this case, z will be concluded to be 0 because it has not seen this yet. But by the time you come here, it has seen x. So you see one value or the other in strong consistency. In weak consistency, you can have an execution where you can have an effect where both these can be returning 0. So in weak consistency, these writes are still in the buffer. So these reads are never able to consult the buffer. So you can get a funny value in a sense that is different from any interleaving, from a value that any interleaving would have created. Okay. So the idea is that you can get a situation where the interleaving based execution is your mental model. That's the only mental model for a concurrent programmer. Concurrent programmers really are thinking of thread doing something, another thread doing something, this thread doing something, this thread doing something. Usually you don't even have to think that way because threads are doing independent work. Why bother? Don't think inside the threads. But sometimes threads talk to each other through variables. Then you have to still think of communications, but it's as if this thread did this, like that order. In weak consistency, these threads did something, then later they are consulting their actions later across each other, but they have never seen their prior actions. That's because those values are still held in buffer. That view is okay, and that view is going to be available for certain important people like operating system designers and so on. They worry about those kinds of details later, or library implementers. So when you don't want weak consistency based views, it's hard to, you can put a flush here, flush here. Flushes push out the buffer. And why weak consistency is being imposed on us? Well, somebody had talked to me yesterday saying he's a hardware designer. I forgot who it is. The news is that hardware designers have been pushing burden on software designers ever since the beginning of history. Don't think that hardware designers are designing the most beautiful chips so that you can write the simplest programs. That is not happening. Hardware designers are fighting such big battles designing $20 billion transistor chips. They have a year or two to execute. Their budgets are so high. They had to sell a chip under 100 watts. So what do? They try to shave off on execution costs at every point. So the weak consistency view is good because you don't need to update cache currency networks unnecessarily and all that. The upshot is that the programmers have to worry about it later. So this has been going on. Multi-core and parallel programming is another exercise. Hardware likes to have multi-core. So expose all the hyper threads out there, put it on the software designer. Now we are having this class because we now had to struggle with the software design. Software design has become extremely hard with parallel programming. It has to become easy again. We are not there yet. So we are in a crisis mode where the entire parallelism has been opened up from hardware, thrown at us in 10 years. And the community has to take at least 15, 20 years to slowly absorb this and come up with better models. And OpenMP is an attempt in that direction, seal some of the complexity. That's how it is. So weak consistency flush got me going because this is another of my favorite areas. So you have to stop me from talking too much. But I work in this area a lot. And we actually tested GPUs recently in a paper where GPUs weak consistency was never made clear by NVIDIA. It got their attention and things are better as a result. So, okay, so OMP flush is a rare construct, but the principle behind OMP flush is important to know because I'm sure you will hear this word one day. What do I have now? I think I can safely say that this is an accelerated course, so not everything can be taught here. But I think the lab sessions are important at this point. So this afternoon we have to go to a lab and then practice the codes out there. I have a few more things to say, but since you have never probably even seen the work that has gone into this course, not that I'm boasting or anything, we did, Professor Jairaj and I did spend some time putting together some examples. So hopefully when you get we were prototyping our work here. A cleaned up version of this directory is made available to you in your accounts, or you can get it. That's the hope. So what did we do? Not boarding pass, that's my boarding pass. Okay, but I just put a lot of things in a hurry there. But we have a folder called HPC Toolkit, JRAG PBS testing, that's not important. PBS Learn, we did a test of that, slide skinnage. Some of this has been ported to in a cleaned up version there. But let us look at the contents of OpenMP. So what we created for you is, so let me just, so we have assignment to OpenMP. This is an assignment I gave to my class. It was fairly successful when I taught it. There are things, get number, threads, Intel examples, that's fun too. Maths and presentation, n-body reduction, papers are there, simple OMP races. So there are classes of examples. Let us look at one. Let's get threads. So it has 2 versions on it, and then with shortcuts. I need to remember what they are. Okay, so maths and presentation. Simple OMP races, CD. Okay, so let's look at an example, simple OMP. As the name of the example says, this is an example containing a data race. This is an incorrect OpenMP parallel form. An OpenMP will not tell you that it is incorrect. That's a problem. So you needed either human intuition to know that there is a dependence across the loop iterations, or sharing between loop iterations, or you apply a tool called Archer, which is what we do. Because in complex codes, races are not very apparent to the human eye. So the idea is that if there is a loop carry dependence, if one loop's updates depends on either the previous or the subsequent iteration. So here the ith value is getting created using the I plus first, and then that value is referenced in the next iteration. So when there is a carry dependence, loops carry dependencies across them, that is when those loops are not parallelizable. Dependence testing is a long topic. I have slides. There is true dependence, which is the value flow dependence, anti-dependence, and output dependence. You need to sort of see whether there could be. The idea is in the class time, we won't have too much time. I can try some more simplified, but the basic idea is, again, try to see if the loop run backwards gives you the same answer. That's a quick test, but for now that is good. But I'll show you some more examples. And how is this pinpointed by the tool? The tool's output is not very. Is this even run under Archer? I don't know. Anyway, the tool thread sanitizer is getting used, but thread sanitizer will be simple races. I don't know whether this is the right directory, but there is a tool that was applied. But let me look at the Archer. Okay, I think that's better. Archer run TypeScript. Yeah, this is where it is. So that example, simple OMP races, was run under the Archer tool. I don't know whether I don't think we got time to install Archer yesterday. And unfortunately, Archer's install takes a little bit of time because we didn't want to assume anything about the environment. So we'll run a script. That's easy. But then after that, you have to do something for 2 hours. And then 2 hours later, it'll be done. Hopefully we can launch it as soon as we go in today, and but there may be a better way to do, because then 40 installs of Archer will be going on. Each will be trying to get LLVM through our network. May not be wise. So maybe we have to get one install and then copy over the executable or something. I don't know what we can do. But if we install Archer, all we need to do is clang Archer simple omp raise.c minus o simple omp raise, and then run simple omp raise. That's how we catch that raise. It'll tell you error. Okay. I don't know, some warnings. This tool is still, yeah. It has a certain output. It tells you in a simple-minded way where I let us read size. I don't know whether this is the. I'll check during lunch break. I like to SSH into my machine, but it actually gives you the line info. Read size of 4 by thread T2, previous write of 3.2. Where's the erase? Error reading. I'm seeing the error reading file. That's not good. Okay, thread sanitizer erase. Thread sanitizer is the technology used underneath. It has to give me line info. Okay, well, we'll have to play easy with Archer till I verify it. I think, yeah, it has been run. Some of these need work. Simple erase TypeScript. I think Archer finally gives the thread sanitizer output. Primes.omp dot. Okay. Intel examples. Let's look at code with races. Why is this a problem? This code is a little bit of a problem. Let us find out how, and let us see how to cure it. I will again catch up on the Archer's output. I need to make an attempt to run that example again. Simple OMP races will produce a messy output, but at least there should be a raise. But I saw an error in reading file. I don't know whether that is part of the message I expected. Okay, but barring that, let's look at this one. Pragma OMP parallel for I equal to 0, I less than number of threads, I plus plus. If I misspoke something earlier, I will correct it now, because what is happening here is this iteration space, all these iterations are being divided by this parallel for. I becomes private to each thread. That's what I intended to say if I didn't say it. I is private. But these variables that are nested below are shared variables across iterations. So J is shared among the threads. Not good. They will contend on J. So there is a data race here. So in OpenMP, Tim Mattson and everybody has written about OMP's parallel pragma and to which iteration the parallel pragma applies. Here, what we are doing is creating a thread team, and the thread team is executing this piece of code. That was clear from discussion so far, right? So the thread team is created here. As many threads there are, they are running here. When the thread team is running here, they are looking at the J variable. This code, as written, has to have some more declarations here. I don't see it. So I don't know whether this is even legally compiled under C, because I am using a J variable. Presumably there is an int I and J before. This is from an Intel web page where they show this is a code with races. And let us look at the corrected code. Then we'll know. modified with races removed. Let's look at it. Okay, let's contrast these two. Yeah, Intel examples came from a web page. I just took the web examples. They are not meant to be full code fragments, but it is giving you a scenario. But let us see how this removes the races. So this is the code with races, wrong. This is code with races removed. What's the difference? Yeah, exactly. Yeah, int j, int k. So that is introducing a local scope. So there, the variable int j is being declared for the benefit of the thread team, and that is a local variable. So there is no contention between the j of one thread and j of another thread. Ergo, also same as j, k of one variable, k of the other. Whereas here, it was this won't compile because j is never even declared. The code's intent is to have j and k declared up here. I also declared up here. But then those are all shared, and they are all racing on each other, j updates and k updates. So this was a point I made very early in my talk itself, that you should scope these variables. And this is exactly the code with modified with races removed, Intel's example. So it's always a gotcha for for OpenMP programmers that they put a for loop and then put a nested for loop, but then they forget that the nested for loop's iteration variable is now shared, unless they scope it. Intel examples are good. There was a pretty good Intel web page. All these companies are important, are interested in code. Some of them I haven't read. I just collected them and put it. Parallel, schedule static, no wait. That's available to suppress a barrier. So no wait attached to Pragma OMP4, Pragma OMP parallel removes the implicit barrier that it puts at the end of it. That's the idea. So there are a lot of these little things we had to do. We can't pick it up all of it, but there are these details. I have some material I do want to get to, but I lost track of time. When are we ending? Huh? 12:30. Okay. In the interest of time, let me show you what the world would have been without OpenMP. I was going to give you that experience before we got this slightly better world of OpenMP, but unfortunately I thought that showing you pthreads in great detail will give you the horror stories of pthread programming without any net benefit you may not write. So pthread programming has a lot of interesting wrinkles, but let me show you a few so that we at least appreciate what OpenMP is doing for us. And one day you may need to write a pthread program also. Set default font 14. Okay. Okay. So simple C bugs. Let us look at the simple C bugs one managed to introduce with pthreads. So yes, simple C bugs, pthread assign output, a leak, pthread leak, pthread debug, pthread pthread I'll just do you a diff. So when I diffed pthread dp leak and pthread dp, the diff shows what the difference was. In pthread dp leak, in the pthread DP there were 3 free statements. After using some variables, I malloced them, I freed them. And in pthread DP leak, they were not being freed. So I was leaking memory. And this is discovered automatically by address sanitizer. I'll show you the output. The outputs of some of these tools need some visual training. They may not be very pretty. Sometimes they show with respect to the assembly code. At least Thread Sanitizer and Archer are supposed to do line level reporting, but pthread simple C bugs, address sanitizer output for a leak, at least it tells you that there is a leak. So when I ran clang or GCC minus f sanitize address, that's how you catch. Why don't you run it? Whenever you have a C program, just run address sanitizer. At least it will tell you there's a leak or not. Then you can worry about where it is. So don't use clang if you don't have clang, use GCC. But the funny thing I discovered yesterday is when you use GCC, the file name has to come first. I don't know why. With clang, the file name and the flags can come in either order. Strange. It took me a few minutes to figure that out, but that's okay. GCC pthread dp.c minus f sanitize address minus lpthread minus lm, because this uses math library. Then you do /a.out. It'll start running the program. Then it says, sanitizer detected memory leaks. So that's how you get an alarm bell saying, oh, there's a memory leak in this code. But then the further printout only shows you the hex addresses. I think you need to read the assembly or generate some other info. It's at least alerting. I haven't done the deep dive here, but that's what it is. I'll ask my students and see how they come to the source line. That would be good. Let's do another diff. I have a ready example. This is still not pthreads. It's this is happens to be a pthread example. You can run it on sequential also. Diff pthread buggy. Okay. Okay. This is another example where there was a little problem, and I'm diffing the file. And this is a common mistake one can easily make, but tools at least tell you that the mistake is there. So the differences are instar malloc size, and in the good code it is instar malloc size star size of int. I do this all the time. You may do it all the time also. What you need to do is malloc, not size times size of the item. Otherwise, you are generating arrays that are not correctly sized. They can have memory overlap between threads regions. So if you want to catch these errors, address sanitizer output overlap. That's how I caught that error. So clang minus f sanitize address, same command. It will start running, and it says address sanitizer heap buffer overflow on address. It checks the heap, checks for things, overflow because you didn't allocate enough size in the malloc heap. So when you are running in your code, you went outside your heap. Usually those things will work correctly for some time. Sometimes funny things will happen on standard output because it starts eating into the processor's file descriptors. A lot of strange things happen. Eventually a good thing like segfault will happen. So the codes like this are, so since we are not using, in HPC we are going to use C and C++ 80-90% of the time. C and C++ needs a lot of careful debugging. I can tell you how many bugs are still left. Yeah. So you need a lot of good tooling. What else? The other thing I'm going to show you is we did a lot of good examples, but I didn't have time to show. Dot product has a lot of, and this will be left for your education, and you can give it in your class. Core dump. Okay, we got a core dump, and there is a core dump.text that explains why that core dump happened. And this is a reality of parallel programming. I ran a parallel dot product on a huge range, and it core dumped on me. And it happened because we were not checking for the number of threads being allocated successfully. We said allocate a pthread create, but then we didn't see whether the pthread create actually created a thread. We happily carried out. And this is all a worry which OpenMP allocates. So somebody asked whether get set number of threads is always going to be obeyed by the OpenMP runtime system. OpenMP will carefully give only the allowed number of threads. But pthreads, you're on your own. So I'm just doing a pthread create, pthread join. Okay, that's bad code. Because I should actually check for the return status of create to see whether a thread managed to get created. Otherwise, you're asking for trouble. Let us look at my programmer's postdoc's code. He immediately improved my code in many ways. So int created equal to pthread create. If created equal to 0, the OS is telling you, sorry, I didn't create it. Then what is it doing? He's basically, it depends on the logic. Create equal to 0, success. So it's carrying out successfully with things. Otherwise, unable to create more threads, going serial. That's a good escape code. If you can't create more threads, please do serially. Serial execution is always available. So this is a dot product which has another nice thing going on. I'll take you a few more minutes. I was chunking ranges into halves. So there was a nice algorithm I created. I was very proud of it. This buddy system of memory allocation where you allocate in powers of 2, I got an inspiration from there, and I said, oh, I'm going to create a if I had to do a dot product in a range 128, I'll try to, or 129, I'll look for the next highest power of 2, lowest higher 128, etc. So I try to create large chunks of work. I had to do that by hand. OpenMP chunking automates that. You don't need to do it by hand. There is another pattern that is easy to create in OpenMP in pthreads, but it's very wasteful. When you have a thread that is running and it has to spawn 2 more threads, if you create 2 additional actual pthread create threads, then you are doubling the number of threads. So this may create yet another 2 copies. So I was creating a binary tree of threads. My postdoc said, don't do that. When the master thread comes here, do 1 thread t new. Sorry. Yeah, thank you. I'm almost done. So t old came in. The old picture was t old came in, and it created t new 1 and t new 2. Okay, that's what I quickly drew here. So I don't need this. My postdoc said, don't do that. When t old comes, create 1 t new, but let t old itself continue. Because it's a thread after all. It's a master thread. So this way you are essentially getting the capability to do 2 items of work, but with creating less threads. And it really shows up in performance. So accidentally you can do a lot of bad things in pthread land, including data races, but including unwanted thread creation. Whereas the master should just spawn threads on the side and the master should keep running. That's a better model. OpenMP is still not a panacea, but OpenMP gives you 50% relief from indigestion gas burns, but the other you have to worry about it later. Okay, a lot of things. I didn't get to MPI at all. I was hoping for some MPI today, but I think we have enough to chew on. I told them what the labs involve, but Friday I'll give you a fair amount of dosage on MPI. Friday I'll be back in action. Tomorrow and day after I'm not. Wednesday afternoon, what? MPI and all. I see. Okay, but I'm not giving lectures, I'm only doing labs, is it? We can do anything, yeah, but my lectures are over for 2 more days, right? Wednesday and am I giving any lectures Wednesday or Thursday? Only labs. But MPI is my favorite topic. I'm key. Yeah. How many of you here are here from far away to learn MPI? Okay, I knew you. How about you? Okay. Yeah, I will. How much MPI can we achieve? Okay, let us see, be realistic. I have 3 or 4 matrix multiplies. Those are good MPI codes because it gradually takes you over from a serial matrix multiply to a row distribution and multiply the rows with another matrix, then get the answers back and pipeline more work and pipeline more work and then shift the occurrence of the MPI weight around the loop. 3-4 optimizations can be illustrated there easily. That's one of my favorite codes. But we have this tool called ISP that was developed by my group long ago, where you can run an MPI program under ISP. It worked for us. So it actually shows the communications between processes graphically. It can be a good intuition, a builder. Then we had to quickly run MPI n-body and OpenMP n-body and just see the effects, okay? But we can leave you with a taste of enough MPI knowledge to know its pros and cons and how to use it carefully and what differences are. I'll be ready full of action for Friday. I had a beautiful, I'll take 10 more seconds. I had a very nice Eclipse integration of MPI debugger, and I had it working on my Mac till Mac's last operating system. But as soon as I upgraded my Mac to Mac Sierra, that virtual machine is not booting. It's bad. So I had to now undo my Mac to an old Mac OS and then somehow get that file out and put it into another virtualizer. But who uses Eclipse? Does anyone use Eclipse? Okay, good. Eclipse integration of these tools is a lovely thing to have. Okay, so I can point you to that. Okay, let's have lunch. Hopefully we'll, in the lab, the plan is I will give you all the worksheets. I showed them roughly what the lab sessions are. We need to quickly have the files installed. I think the files are available in everybody's account. How do they do it, FTP or what? I can switch. They can FTP? Okay.